Little announcements. We have, I don't know if you've been paying attention to the calendar. Our next test is a week from today. So that will be your next chance to get some more checks off of your list. I hope that everybody is understanding the way that the grading works for the tests. You should by now have looked over your first test results, which you can see in the Gradescope. If you click on your first exam in there, you will be able to see which questions you got right and which questions you didn't get right. For the ones you didn't do right, you will see some comments from me also. So you should hopefully have your big checklist on paper, and you can bring that to the test with you next time, which will tell you, which questions you have to do. If you already got a check, then you don't have to do those questions on the test. Anybody, any questions about the setup there? All right, it'll be great. I'll say some more about it next time, I suppose. Okay, so we're talking about weighted voting. That's what we started with last time, and we're going to do a little bit more details this time. Weighted voting. Is this? I'm thickening it up. Is that better? I don't know. Weighted voting is what we're talking about. So I hope you recall. It's been a week, I know, but this was examples like this kind of a thing is what they look like. This is an example of a weighted voting system in which, so the meaning of all of these numbers, I hope you remember, this is a system in which there are 4 voters. These right here are the voters and their weights. Voters and the weights. Well, it's really just the weights, I suppose. There are 4 different voters, and those are their weights. I think I liked it thinner better. These are the weights of each of the voters. The weight means basically like how much your vote counts. So we have one person whose vote counts for 5, one person whose vote counts for 4, and then 2 people whose votes count for 1. And then 10 is the quota. And the quota is how many votes you need in order to actually like pass the law or whatever it is they're voting on. You got to get to 10 in order to win the vote. All right. So we have the quota and the weights, and the what this is similar to most of sort of big corporate voting. This is the way they do it. People vote in proportion to their ownership of the company. So someone who owns 30% of the company, maybe their vote counts for 30 or whatever. This is also the way that the Electoral College system works. Basically, every state has a different weight, and then you add up the weights. You don't actually, when you're electing the American president, you don't actually add up the votes of the people. No, that would be too straightforward. Instead, you do this weird Electoral College thing with the points. All right. Anyway, that's the basic setup. And the big question that we're trying to ask throughout this whole section is, how can we measure each voter's power? And there's sort of an obvious but wrong answer. The obvious but wrong answer to this question is you just look at the numbers. The 5 is more than the 4. So the 5 has a little bit more power than the 4, and then both of them have a lot more power than the 2 ones. But actually, that's not always a correct way to analyze the situation. In this case, that's not correct. Actually, in this case, we talked about this example last time. Here, the 5 and the 4, the 5 and the 4 actually have equal power. That's because in order to make it to 10, you need to use the 5, and you also need to use the 4 plus 1 of the 1s, right? But in any case, in order to get to 10, you have to use the 5, and you also have to use the 4. There's no scenario in which the 5 being 1 more than the 4 actually matters for anything, right? So in this case, the 5 and the 4 have equal power. I'm going to switch back to my slightly thicker. I like it better. The 5 and the 4 have equal power here. And each of them have much more power than the ones. All right, but the ones still matter in this case. The 5 and the 4 have equal power. I will just say the ones still matter. For example, e.g., you can do like 5 and 4 and 1. We'll make it to 10, right? So this is one scenario in which one of the ones could make a difference. The 5 and the 4, and one of the ones can make it to 10. All right? Yes?
Shouldn't the 1 have just as much power as the 5 and the 4 to make it to 10? Or no, because it's a smaller number?
This is a good question. Maybe the 1 also has just as much power. I would say there is a difference because, for example, and this is this may be a source of some confusion as we go forward. But in this example, in order to make it to 10, you must use the 5. You also must use the 4. I could ask, must I use this one right here? The answer is no, because I could use the other one. So the 5 and the 4 as individuals are necessary to make it to 10. The ones are not. As individuals, they are not necessary to make it to 10. One or the other is, but not each of them. All right. This is a subtle point. Okay. So last time we discussed 3 simple ways to talk about power in these systems. They were dictator, dummy, and veto power. So I want to just refresh our memory about those, and then I have some examples for you all to try. I'm going to walk around and see what you think. Dictators, dummies, and veto power. So dictator means, this is this sort of the easiest one to analyze. Dictator. This is someone, one voter who can meet the quota by themselves. That is like their weight is already equal or bigger than the quota. That's called a dictator. And a dictator is, that's very easy to tell. When you look at the numbers, just one of the numbers is greater than the quota. So an example would be something like, if I have, say, 10, but then 11, 5, 1. Is there a dictator here? Yes, the 11 is a dictator here, and the others are not. That's because the 11 can meet the quota already all by themselves. So this 11 is a dictator. All right? It's always very easy to tell if there's a dictator. Okay, what about a dummy? A dummy is kind of the opposite. A dictator has like all the power. A dummy has no power at all. So dummy means this is a voter whose vote can never matter. And this would be a scenario like something like 10, and then how about 5, 5, and 1. In this case, the 1 is so weak that actually it never matters if the 1 either votes towards the quota or against. It cannot have any effect on anything. The only way you get to 10 is if both 5s say yes. And then at that point, the 1 doesn't matter anymore. So here, this one is a dummy.
Oh wait.
Yes.
I don't know if that's entirely true. If the first 5 and the second 5 disagree,
yeah,
then the 1 could break that tie, right?
I don't think so. Like if the first 5 says yes, the second one says no, then you still can't make it to 10. You have to think about these numbers. The people who are voting have to add up to 10 in order to make it work out. So if the 5s disagree, then you're only going to get one of them. Say this one says yes, and then the 1 can say yes. It's not going to break the tie though. So it'll just go up to 6. You still won't make it to 10. Right? It's not actually about count. You don't actually count up how many people said yes and how many people said no, and whoever got more is the winner. Then it could be like 5 to 6, but you got to make it to 10 in order to pass the vote. All right, so that's what a dummy is, a voter whose vote can never matter. And then the third and final thing, this is maybe the most subtle, is called veto power. And this is a scenario actually like the one that I wrote at the beginning. 5, 4, 1, 1. This is Sorry, I meant to write the words first. Can I write the words first? This is a voter whose vote is necessary to meet the quota. You need them in order to get to the quota. It doesn't mean they can make it all the way themselves, but you need them in order to get to the quota. So in this example here, 10, 5, 4, 1, 1, both the 5 and the 4 have veto power here, because if you want to get to 10, you must have the 5 and the 4. All right? Whereas the 1s individually do not have veto power. So here, the 5 and the 4 have the veto power here, because their vote is necessary in order to make it to 10. All right? The 1 does not have veto power. That's because this one by itself is not necessary to make it to 10. You could use the other one. And similarly, the other one is not necessary to make it to 10 because you could use the first one. So 5 and 4, in this example, 5 and 4 have veto power, and the 1s do not. All right. This is slightly confusing because it is true that you need one of the 1s in order to make it to 10. But as individual voters, neither of them is necessary in order to make it to the 10. All right. Any questions about that? I have a bunch of examples for us to try. This would be a typical, this is one of the lines on the checklist, dictator, dummies, and veto power. So a typical question would be, I show you one of these, and I say, is there anybody here who is a dictator? Is there anybody who's a dummy? Is there anybody with veto power? Let's check it out. How about, let's just do one more all together, and then we can, and then I'll give you a bunch to try. How about this? The 30, 10, 10, 10, 9. First of all, is there any dictator here? No, the dictator is very easy. That's just somebody whose vote is already equal or greater than the quota, and there isn't. So there is no dictator. Is there any dummy? That is a voter whose vote doesn't matter at all. What do you say?
Yes.
Yes.
Be the 9.
The 9. Yeah, if you just think about, just look at the numbers, it seems like maybe the 9 is only slightly less powerful. Actually, the 9 has no power at all in this case. If you think about how could you make it to 30, the 9, there's no scenario in which the 9 actually matters. So I should be writing this down. There's no dictator. The 9 is a dummy because there's no way that 9 can matter. Does anybody here have veto power? That is, any individual who is necessary to make it to 30? Yeah?
All 3 10s.
Yeah, each of the 10s has veto power. So each 10 has veto power. Actually, it's not so hard to see. The only way you can make it to 30 here is if you have all 3 10s together. And the 9 doesn't matter either way. Each 10 has veto power. That's because it is necessary in order to get to 30, it is necessary to use each of those 10s. All right? Here's a simple variation. What if instead there was just like one more person? 10, 10, 10, 10, and 9. Does that change anything? First of all, is there still no dictator?
Yeah,
There is still no dictator. Sorry for the double negative type question. But yeah, none of these voters makes it to 30 by themselves. So still no dictator.
But I don't know if any of them can single-handedly veto.
Yeah, we should talk about the veto power is the one which might be different. Can we just say, is the 9 still a dummy? I think the 9 is still a dummy. There is still no scenario in which the 9 actually matters to make it to 30. So no dictator, 9 is a dummy. What about the veto power? The question that you ask yourself, before each of these 10s was necessary, I should ask myself, is this 10 right here necessary to make it to 30? I would say no, because you can use the other 10s to make it to 30. All right? Is that a question?
Technically, none of them have veto power.
That's right. So in this case, there is no veto power. Now, it's still true you need 3 10s to make it to 30, but no one of those 10s individually is necessary to make it to 30. This is a little slightly confusing in my opinion, but it's true. No veto power. This is because no single 10 is needed to get to 30. All right? I will just say parenthetically, you can use the other ones. right? Okay, anyway, I got 3 for you to take a look at. I got 4 for you to take a look at. See what you think. In each case, your job is just to decide, is there a dictator? That's always easy to decide. Also, is there anyone with veto power? Is there any dummies? I'm going to make the quota 10 every time, just to simplify things. So think these over. I'm going to walk around and see how you feel. I'm here to help. You don't have to talk to me if you don't want to. All right? So in each case, tell me, dictator, dummies, or veto power? Is there any, and if so, who? Feel free to chat with your friends about it.
Is that meant to be a 14? Because that looks like exclamation 4.
14, yeah. My pencil left the page a little bit. Dict, dum, veto for each one. I think I have a typo in the first one. It mostly doesn't matter, but I'll say why.
But if it would be 9?
Yes, but this is actually, I'm going to change the 9 to a 4. I'll tell you why later. Yeah, if it was a 9, then it wouldn't. But there's a problem with that. I'll say. Good. Yes.
Like, to meet the quota 7, like 7 really necessary.
Yes.
So it's actually vote for, so
Yep.
any votes. So 14 for this one, so maybe 7.
any dictator is automatically. Okay. Yeah, right. Yes. Yeah, actually, it's automatically, if somebody's a dictator, they automatically have decisions. Because you need this. All right, let's talk about these. So the first one here, the first one is the simplest. That's the only one which has a dictator, and it is the 14 is a dictator in this example. So this one here, sorry. Trying to erase. All right. In the first one, the 14 is a dictator. Automatically, actually, if there's a dictator, they automatically also have veto power. You need the 14 to make it to 10. So this is also has veto power, is the 14. Is there any dummies? Yes, actually, this is a fact which is always true. If there is a dictator, then automatically everybody else is a dummy, right? Because a dictator is one who their vote is the only one that makes any difference, which automatically means that everybody else doesn't matter. So the dummies are 4 and 1. All right. Maybe I should, yeah.
If you had the 9 there.
Yeah, I was just going to say, what about, so when I originally wrote it, I said this, and then I said, actually, there's a problem with this. We talked last time, do you have a?
Yeah, I was going to say the problem is that technically, even though the 14 can automatically make the quota, if the 9 and the 1 vote against it, they also make the quota.
Yeah, right. This should seem weird because 14 is more than 10, and so from that point of view, the 14 is a dictator. But actually, in this arrangement, even if the 14 says no, the 9 and the 1 can vote together and make it to 10, which suggests that the 14 is not a dictator. The issue is something that we talked about last time. This was a technicality about what the quota is allowed to be. The quota is not allowed to be so big that you can never reach the quota, and it's also not allowed to be so small that, if you remember the rule, it says that the quota has to be at least 1/2 the sum of the weights. And actually, in this example, the quota is too small in order for this to be a valid scenario at all. So here, this was a rule that I wrote last time, is that the quota has to be greater or equal to, I think, just straight up greater. It was this. If you look back in your notes, you'll see this. This is a rule that that is violated in this case, because in this case, if you add up 14 plus 9 plus 1 is 24, and half of that is 14, and the quota is smaller. So this is supposed to always be true. In this example, the quota is too small, and so this doesn't even count as a real example. This is why this weird analysis about the dictator and the dummies doesn't quite work properly in that example. I'm not going to try to screw with you and give you examples like this on the test or on the homework, because that's not even a valid example in the first place. So my apologies for my error. Any questions about that? All right, let's continue with the other ones then. I think we did. So that was the first one. Okay, how about the second one here? Any dictator? No, there's no dictators in any of the other ones. How about anybody with veto power? You just have to look. I'm going to look at the 5 to begin with. The 5 is the strongest. What do you say?
I'd say both the 5 and the 4, if you don't.
I think the 5 is definitely necessary to make it to 10. So the 5 has veto power. What about the 4? You got to ask yourself, do I need the 4?
No, with the 4, I take that back.
Yeah, I think you do not need the 4 to make it to 10, because 5 plus 3 plus 2 makes it to 10. So the answer is just 5 has the veto power. All right, 3 and the 2 you could think through, but they're less than 4. So if the 4 doesn't, then the 3 and the 2 also don't have veto power. All right, I hope everybody said that. And then, are there any dummies here? Anybody whose vote can never matter? Yeah, you should. Your eye should be drawn to the 2. I mean, that's the weakest one there. But the 2 sometimes does matter, because you can go 5 plus 3 plus 2 makes it to 10. So there is no dummies here. Dumb. No. All right? I hope that's what you said. The next one. Also, no dictator here. Anybody with veto power. To make it to 10, I think you need the 7 to make it to 10 because everybody else added together is only 8, so you must have the 7. What about the 3 here? Do you need this 3 to make it to 10?
I would say no because you can use the other one.
Yeah, you do not need this 3 to make it to 10 because I can use the other 3 to make it to 10. This 3 and the 7. So as for veto power, the 7, but not anybody else. Not the 3, not either of the 3s, and certainly not the 2. And then we should also think about, is the 2 a dummy or not?
Yes, it is.
I think yes it is. I don't think there's any way you can add up to 10 which actually uses the 2.
Is the veto like the number that you need? Like, to make it?
Yeah, I think.
Alright, I was just confused about it.
Yeah, veto power means, so like when I say 7 has veto, it means that this 7 is necessary in order to make it to 10. Is that what you meant by?
Yeah.
The 7, you need the 7, yeah. It's a little confusing though. The 3 does not have veto power because you don't need this 3. You need one or the other of the 3s, but you don't need each one individually. Yeah. Okay, so the 2 is a dummy here. I think that's what we said. Dumb, 2. All right. And then the last one. What's the difference between these two? The only difference is it has 1 fewer 3. Can anybody see what difference that makes? What do you say?
The 3 has veto power.
Yeah, now the 3 has veto power. In this example, we have this thing where like this 3 is not necessary because you could use the other one. But this time, actually, there's only 1 3, and you got to use that 3 in order to make it to 10. So this one has no dictator, no veto power. Would be the 7 and the 3. And then the 2 is still a dummy. There's still no way that this 2 makes a difference here. All right, excellent. Any questions about any of those? I hope that those seemed all right. You'll have some more of these to look at on the homework. This is a very basic way of analyzing the power relationships. Maybe could we talk just briefly about the Electoral College in the United States? The U.S. Electoral College. I believe you need 270 electoral votes to become the president. So that the quota in this system is 270. And then the weights, there's like many different weights here. And I wrote down some of them last time. I will refresh my memory. The top one is California, which has 54 votes. The next one is Texas, which has 40. The next one is Florida with 30, etc. Down to the very smallest ones, the small states like Delaware, etc. are 3. 3 is the smallest. Now, without knowing, you can't say for sure if you don't know all of these numbers, but first of all, is there any state in the Electoral College which is a dictator? No, that would be a state where they are the only ones that matter and they can elect the president just all by themselves. That is absolutely not possible. And if that ever, so let me just say, no dictator. You know, the weights, like these numbers over here, the weights of the states, they change over time. They can increase or decrease depending on the changing populations of the states. The California has the most because California has the most people in it. And in theory, one of the states could grow so big that its number goes up all the way up to 270. That actually is possible in the rules of the Constitution. That would make that state into a dictator, but that basically would never... the other states wouldn't stand for it, but yeah.
They'd also change the quota if that happened. Isn't the quota like just over half of the total possible?
Yeah, so I think when these numbers change, some of them go up, but some of them go down. The quota doesn't change over time. I think that that's true. I'm not a constitutional expert, but I believe the quota would change if there were a new state. Then it would, I think those are the rules, but yeah, I don't know. Anyway, there's no dictator. What about veto, or question, yeah?
Yeah, this might sound stupid, but are the weights of like what each state gets like based on like aggregate population or just like the voting?
No, it's based on the population.
Just in total?
Yeah, the total population of the state, yeah. According to the latest census. So these numbers actually just changed this year because there was a new census last year, something like that. Okay, what about the veto power? Yeah?
I would say, is there no veto?
That's right. Can you say why?
Just like felt like the right answer.
Yeah, it does. Like, it would actually be kind of messed up in the real world if there was a state that had veto power. But what that means, you should naturally look at California. Is it true that California has veto power in the Electoral College? That means, like, if you want to become the president, you must win California. Is that actually true? No, it's not actually true. You don't have to win any of the states. If that were true, that would be a messed up system. I mean, the Electoral College, plenty of people think it's messed up anyway, but it's not that messed up. You don't have to win California or any other state. So there's also no veto power. Is there any dummy states? Like the 3, for example, the Delaware. Is Delaware a dummy? That's quite a small number. Any idea?
No, not in the proper sense. I don't know if Puerto Rico would count because they technically can't. I don't quite remember their ability to be able to vote on a president, but I don't think there's any true like dummy states.
Yeah, she's right. There is no actual dummy states. It is true the 3, like Delaware, has a very small amount, but it is still, in theory, possible for these small states to make a difference. There is no total dummy state. Actually, again, if there were a state which became a complete dummy, then people would become outraged and change the rules, because that's not supposed to happen. The only, as she mentioned, Puerto Rico gets no Electoral College votes, even though they are citizens of the United States. That is also messed up in my own personal opinion, but this would be like if for some reason people who lived in Vermont didn't get to vote for the president. Why not? I don't know. They just don't. That's the state of Puerto Rico these days. Anyway, no dummies, right? Except Puerto Rico and Guam or whatever. There are a few United States territories that don't get to vote for the Electoral College. All right. Yes, I think if, as a historical, societal, political point, if any of these things actually happened, like if there was a dictator or a veto power or a dummy state, immediately the rules would be changed, because this would be unacceptable. If there really was a dummy state, that would be, I would say, fairly undemocratic if you just have one of our states that's not allowed to contribute to the Electoral College. Yeah.
So even though there's technically no dictators, vetoes, or dummy states, what's up with swing states then? Because swings, like, it's usually whenever, like, anytime there's an election season, it's usually for them, like, California usually gets blue, Texas gets red, or whatever, but then people focus on, like, 5 states, like, usually Pennsylvania and a
Right.
couple other ones.
Yeah.
Why are they such a
Yeah, it is. Actually, when you like listen to politics around presidential elections, it is common for people to say things like, you have to win Florida if you want to become the president. That is not a mathematical fact. That's more of a political kind of a statement. That Florida is very important. Florida is this 30 here because of the way politics is nowadays. The California is always going to be a Democratic state in terms of the Electoral College. Texas will always be a Republican state. This is just the way that those politics in those states are right now. Florida really could go either way. It's sort of so close in terms of the way that people vote there that Florida is something that we don't know how the Florida is going to go. And what that means from a political point of view is basically this 30 sort of achieves more importance than the other two, not in a mathematical sense, because obviously California is going to be more than 30, but in a political sense, it becomes more important for the politicians to concentrate on these 30s because they're sort of up for grabs, whereas these ones are reliable in one camp or another. Yeah.
So could you then argue then, just because maybe California or Texas has more, I guess, power overall, as an individual voter, you would have more power in Florida though, versus just you're automatically, it doesn't really make a difference if someone's automatically.
Yeah, no, that's right. It's more. I used to live in Pennsylvania, and I had a friend in grad school who was like obsessed with politics. And he heard I was moving to Pennsylvania. He's like, "Oh yeah, your vote's really going to matter there." He lived in California, where it's like, it's going to be Democratic anyway. It doesn't matter. So yeah, my vote in Pennsylvania mattered although me as an individual, my vote matters very little anyway. But yeah, it's true. It's actually true. The people in the very small states, in terms of the weight of their vote in the Electoral College, is even more than these other ones, because the super small states have very small populations, but they still get 3 electoral votes. Yeah. These are weird things that people in politics like to talk about. We're not going to talk too much about that. All right. What I want to talk about for the remaining of today and next time also is a more sophisticated way to judge power. Like this dictator, veto, dummy, those are like 3 fairly simple categories that you can put the voters into, but oftentimes there's just none of any of them. Like in the Electoral College, there's none of anybody. All right. What we would really like is some kind of I will say we need a more sophisticated. This dictator dummy thing is kind of like all or nothing, and usually in most examples, everybody's kind of in the middle somewhere. That's not to say everybody is equal. They are not equal, but they are somewhere in between dictators and dummies and veto. So we need a more sophisticated measure of power. This is what we're going to refer to as a power index. The idea here is I could give you something like, one of these, say 10, 5, 4, 1, 1. And in this case, just because this is a fairly simple example, you can just look at the numbers and figure this out. But we had already decided the 5 and the 4 have equal power here, and the 1 and the 1 have no power here, right? I think this is what we decided together. The 5 and the 4 have equal power, and the 1 and the 1 have no power. In this case, the true power index here is like the 5 has 50% of the power, the 4 has 50% of the power, and the 2 1s have 0% of the power, all right? What I would like to do for the rest of today and next time also is talk about how could you actually figure this out in a more sophisticated example. Is there some kind of formula that you could plug all of these numbers into to give you the actual amount of power that they have? Not just what these numbers are, because the numbers on the surface can be misleading. But is there some kind of method to give you the actual power that they have? All right, and this is called a power index. And actually, there are 2 popular ways of doing this. So we're going to talk about 2 ways to do it. And in fact, they give you 2 different answers. So there's 2 ways to do it. Unfortunately, they both are named after people, and you just have to remember which is which. 2 ways to do it, and each is I would say, sort of a different definition of power. The concept of power, it's not a mathematical notion fundamentally. So there are different ways that you can think about power mathematically speaking. There are 2 ways to do this. Each is a different definition of power. And so they give you actually different answers. And which one is better than the other, you just have to, I don't know. They're just 2 different ways to measure power. And you have to decide for yourself which one you like better, I suppose. Like I said, they're both named after people. The one that we're going to talk about first, and then we'll talk about the other one next time, is called these are 2 people's names. Shapley Shubik. The Shapley Shubik Power Index. All right. This is a method. It's not really a formula because it's a little more complicated than a single formula. I'm not really big into formulas anyway. The Shapley Shubik Power Index. It's a way of telling the true power of each of the weights in a weighted voting system. It's a way to measure the true power of each voter. All right? And as I've said many times, you cannot just look at the numbers. The numbers often are misleading about who has what percentage of the true power, all right? But that's the purpose of the Shapley-Shubik power index, okay? So we have to think a little bit abstractly about how do you tell who is powerful in one of these weighted voting systems. How about the measure of power that's used is, for the Shapley-Shubik, it's a little different for the other one, but for the Shapley-Shubik, the way that we're going to measure power is who can, nice ringtone over there. I always try to make fun of people's ringtones when their phone rings. I couldn't think of anything cute to say other than nice ringtone. That wasn't all that incisive. Anyway, the measure of power that we use for the Shapley-Shubik is who can cast the deciding vote. And this is the point at which you can agree or disagree that this is a good way of measuring power. But this is certainly one way of measuring power, is trying to figure out who casted the deciding vote. For example, in this weighted system, let's say the quota is 6, and then my weights go 3, 2, 1, 1, 1, like that. All right. Now, when we do the Shapley-Shubik, it is convenient to give names to the voters, and I'm always just going to call them A, B, C, D, E. It's helpful to have the names just because you want to be able to tell the difference between the 3 different ones. So it's not helpful to just call the 3 ones. You can't call them all the same thing. You have to keep track of the difference between them. But anyway, my voters here are A, B, C, D. And we imagine, in order to think about this business about the deciding vote, we imagine that they vote in some particular order. Like, for example, in this case, I'm just making this up, B, A, C, D, E. All right? Let's imagine that they're voting in this order, and let's just imagine also that they're all voting yes. And then the question is, whose vote actually makes it to the quota? All right, and that's the person who is sort of casting the deciding vote. So this is not so hard to figure out. I go, this is B, A, C, D, E. If I were to write the numbers, it's 2, 3, 1, 1, 1, right? In that order. And then, so this is not hard, but you have to like tell your roommate to shut up while you're doing this. I'm going to add up these numbers as I go left to right and see at what point is the quota reached, which is 6. All right, so as I go across here, I'm going to look at the 2. Okay, the 2 does not make it to the quota. Over to the 3. Now I have 2 plus 3 is 5. Still does not make it to the quota. Next is the 1. 2 plus 3 plus 1 is 6. And at this point, the quota is actually reached. And so I say this person right here is the important voter in that particular arrangement. Here, C. This is called, so the terminology we use for this is C is the pivotal voter in B, A, C, D, E. Of course, it matters what order they go in. If I wrote them in a different order, it'd be somebody else would be the pivotal voter, right? But in that particular ordering, B, A, C, D, E, C is the one who actually made it to the quota. This is, so the procedure is you have to just add these numbers up as you go across. In this case, C was the one who made it finally to the quota, all right? So a little bit of terminology here. This is called the pivotal voter. This sort of BACDE is one of many possible ways that you could reorder them. You could write them in any order, and it'd be a different pivotal voter each time. The terminology we use for this is BACDE is one of many possible voting permutations. All right. So a permutation, this is a mathematical word which means just some way of rearranging things or some way of putting things in a different ordering. That's called a permutation. All right? And this is one way. There's nothing special about this. I just made this up. All right? The Shapley-Shubik, or let's just look at another example. Another permutation. I'm usually going to call these perms. Another perm. C-E-B-A-D. Who is the pivotal voter here? Write out the numbers. Sorry, I've scrolled past the numbers by now. They're way up there. C-E-B-A-D, that would be, this is 1, 1, 2, 3, 1, right? And in there, again, I'm going to read these numbers from left to right and add up as I go, and I want to know at what point do we reach 6. Can anybody say? Which of those numbers, as you're adding them, makes it to 6? What do you say?
30.
Yeah, it's the 3. I go 1, 1 is not enough. 1 plus 1 is 2, still not enough. 1 plus 1 plus 2 is 4, still not enough. 1 plus 1 plus 2 plus 3 is 7. That makes it to the quota. So in this case, 3, that is B, is the pivotal in this case. All right. How do we do the Shapley-Shubik overall? So the way that you get those overall percentages is, I will say for the Shapley-Shubik, maybe I'll just write this as a definition. Huh? I erased. Okay. This is the definition of the Shapley-Shubik. The Shapley-Shubik. I'm always going to write SS from now on. The SS, Shapley-Shubik, power index of a voter. It ends up being a percentage. That's what we're looking for. A percentage of the total power that they have. And this is the fraction of the time that this voter is pivotal among all permutations. All right. Remember, the permutations means just another way of rewriting the things in a different order. And each individual permutation, each individual ordering is not meaningful by itself. But if you look at all possible ways of reordering them, and then see who is going to be pivotal the most often in all of those different ways. That's how you do this Shapley-Shubik thing. All right? I got 2 examples, and then I got one for you all to try. This is not, in my opinion, not hard, but it'll take you a few minutes to do, and you have to kind of concentrate when you're adding up those numbers. Here's how we do it, though. So let's try 16, 12, 10, and 5. All right? And I'm always just going to give names A, B, C like that as we go. 16 doesn't get a name because that's the quota. That's not one of the voters. All right? And I said it's the fraction of the time that the voter is pivotal among all permutations. So what we have to do is write down all possible permutations of A, B, C. So we need to consider all permutations of A, B, C. That is all the different ways you could write A, B, C in different orders. And there's a few of them, I guess. So I'm going to make sort of a chart here in 3 columns. Once you know what you're doing, you don't have to write your chart in exactly the same way that I do if you don't want to. But anyway, first of all, on the left side, I'm going to list vertically all the different permutations, the perms of A, B, C. So that would be, one is A, B, C. I'm going to try to write all different ways I could reorder them. And I would like to do this in a somewhat systematic way just so that I don't miss any. ABC is one. Another way that I could start with A would be ACB, right? Those are the 2 possible ways you can rearrange it starting with A. Now I can also do 2 ways starting with a B. I could do BAC or BCA. All right? Those are all the ways you can do it starting with a B. And then I can do 2 ways starting with a C, and that should be it. So I could do CAB and CBA, right? These are actually all the permutations. I sort of wrote them in alphabetical order, if you like. If these were real words in the dictionary, that's the order that they would go in. All right? If you have 3 things, then there will always be 6 permutations. You got to make sure you don't miss any. Okay? Okay, next, I want to decide for each of these who's the pivotal. Now, just to help me out a little bit, I'm going to make another column of just the weights of ABCs written in that same order. So this is 12, 10, 5. Remember, A is 12, B is 10, C is 5. And I'm going to write the weights in the appropriate order. So the next one would be 12, 5, 10. The next one would be 10, 12, 5. Sorry. 10, 5, 12. 5, 12, 10. And finally, 5, 10, 12. I think I got it. All right, and then I am going to write down, now it's not so hard to figure out who is the pivotal in each of these rows. So now is the time when you tell your kid to stop practicing their drum lessons. Go across here, you add the numbers up in order. My kid plays the drums sometimes. The drums are in the basement, but where the drums are in the basement is directly underneath the kitchen, and it's very loud in the kitchen when they're doing the drums. It's okay. Go across here, add as you go. The 12, and remember 16 is where we're trying to get to. The 12 does not make it, but 12 plus 10 does make it, so the 10 is pivotal here. So B is pivotal in the first row. And you have to think this through 5 more times, all right? This is why I said it's not really hard, but it's like you have to kind of concentrate on it. So the next one, 12 and 5 and 10. I believe the 5 is the pivotal here because 12 plus 5 is 17. So that would be C. The next one, 10 and 12 is 22. The 12 made it. So that's A, right? Maybe I'll circle the pivotal every time. Is it always just going to be the second one? No, actually, in the very next row, the 10 and the 5 does not make it because the quote is 16. So you got to go to the 12. So the 12 here is pivotal. That's A. All right. In the next one, 5 and 12 makes to 17. So that's A. And then lastly, 5 and 10. Again, 5 and 10 at the beginning is not good enough. You got to go to 12. And that's A. All right. This column here, this is the point of the Shapley Shubik. This column here tells you exactly what the power looks like. You see that A is capable of being pivotal 4 times, whereas the other 2 are capable of being pivotal only once. We're basically done with the work at this point, but I said in the definition here, the power index, the Shapley Shubik, is the fraction of the time that this voter is pivotal. So my final answer here is A is pivotal 4 out of 6 times, B 1 out of 6, C 1 out of 6. And that's my final answer. If you like, if you have a calculator, you can convert this to percentages. I would just do 4 divided by 6. On your tests or whatever, I won't expect you to do this, but if you want to write this as a percentage, this would be 66.6 repeating percent. These ones are 16.6 repeating percent. All right, if you'd like to write them as percentages. If you're actually doing this in the real world for some reason, you probably want to tell people your answer in terms of percentages because they'll understand that better than the fractions probably. All right, I would expect you on our test or something, that's your final answer. I don't care if you know how to reduce fractions. 4/6 is the same as 2/3, but I don't care about that. All right, any thoughts about this? I hope that you are agreeing with me that this is, I would say, not really hard, but it'll take you a few minutes to work out all the details. And it's not just like, can I just plug everything into a big formula? Not really. You have to go through this. This business is not expressible as a single formula. All right, let's try one other example together, and then I got one for you all to try, and I will walk around. Oh, let me just in case it's not completely clear, where exactly do those fractions come from? Each one is a fraction where the top is the number of times, sort of the number of times this one is pivotal. So you look in your chart, and I saw A was pivotal 4 times in the chart. That's why A has the numerator, that's the number on top, was 4. And then the bottom is divided by the total number of permutations, which was 6 in this case. All right? That's how you write your final answer with the Shapley Shubik. If you want, you can reduce the fraction or write it as a percentage, but I don't care about that. Okay? My conclusion in this example would be the A has a lot more power, the B and the C have equal power. That's how it is. All right? Okay, let's try one more all together, and then I got one for you to try on your own sum. How about 12, 8, 7, and 1? All right, let's see if we can do the whole procedure. I call them A, B, C, just like before. So I first write the perms, okay? The perms actually are always going to be the same from one example to the next. I mean, from the previous one to this one, it's the same reorderings of A, B, and C. And I'm basically always going to write them in this order. If you start mixing it up, you're liable to forget one or list one twice or something, which will screw up your answers at the end. Then I got BAC, BCA. There's 2 starting with A, 2 starting with B, 2 starting with C. All right, then the weights. I'm just copying the weights in that particular order. If you're some kind of Shapley Shubik wizard, you might be able to skip some of these steps in the chart, and that's fine with me, although it's a little complicated to keep it straight when 2 of the weights are equal to each other. Things get a little confusing to skip steps in your head, but I will leave it to you to be responsible. 7, 8, 1, 7, 1, 8, and then 1, 8, 7, 1, 7, 8. All right. And now I go down the list here and add the numbers up left to right and see at what point do we reach 12. In the first line, it's the 7 which makes it. That's B. So this is pivotal. First was the B. In the next line, the 8 doesn't make it. 8 plus 1 is not enough. I got to go 8 plus 1 plus 7. That's the B again. All right, the next line, 7 doesn't do it, but 7 plus 8 will make it. So 8 is the pivotal here. That's A. In the next one, I believe it's 8 again. 7 plus 1 is not good enough. You've got to add them all up. That's A again. And then 1 and 8 is only 9, so I got to go to the 7. That's B. And finally, 1 and 7 is only 8, so I got to go to the 8, which is A. All right. And my final answer then is... What do you say? What's the fraction for A? Yeah?
3 out of 6.
3 out of 6, also known as 1/2, also known as 50% if you prefer. B also gets 3 out of 6. And C, 0 out of 6, which means 0. So actually, if you didn't notice before, it is true. C is a dummy in this example. C has 0 power. And if you look at the numbers, I think you will agree, there's no way that 1 can make any difference. All right. The Shapley Shubik will tell you if there's anybody with, if there's any dictator or a dummy, just by how the numbers work out at the end. All right. Any big questions? I got an example for you all to try. Let's see what you think. How about 12, 7, 6, and 5? Here, I'll leave that one up there maybe. Can you see it all? You basically want to do this stuff again, but it's different numbers, so it'll work out slightly differently at the end. I'm going to start doing it up here. Spoiler. I'll give you another minute. See what you think.
Yeah. Okay. Okay.
All right, can we talk about it? Maybe, I know I don't do this very often. Maybe we could just, could I just go like across the back row perhaps and shout out who's the pivotal each time? I hope you did it in the same order that I did, or else you might be confused. Is that all right? What'd you get for the first one?
B.
B. Yes, I meant to start in the corner, but somebody said B. Yeah, B is what I got for the first one. Somebody else want to shout it out?
C.
C was next. Yeah, my plan to go across the row failed miserably. What's next? A. Yes, I agree. And then A. I think actually all the rest of them were A's. So if you did it in the same order, these are what you should have got. I think
That's not what I got.
it's not what you got.
I got
We can fight about it.
B as the second to last.
B here.
Yeah.
So for this second to last one, I need the 7 is what makes it to 12. It's very easy to mess these up, just because you're doing the same thing over and over again can get a little
No, yeah, I was
a little
wrong.
confusing.
I had it wrong.
Yeah, I think this is correct. B, C, A, 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 A. All right, if you did it in that order. So my final answer then would be A is 4 out of 6, B is 1 out of 6, C is 1 out of 6. All right, again, this indicates that the 6 and the 5 have equal power, and the 7 actually has much more power than either the 6 and the 5. Yeah.
The homework or test is 3 the most votes that we're going to get, so we'll most have 6 permutations.
Yeah, so this is actually something I wanted to talk about in our remaining 10 minutes or so is what if there's more than 3 voters? Actually, you will have, say if there were 4 voters, you actually would get quite a bit more permutations in that case. I would say on our homeworks or tests, I might go to 4, but not beyond that. Doing it with 4 is kind of the limits of my patience. In theory, you could do it with bigger ones, and if you're using a computer, you could go quite a bit bigger, but yeah, by hand, 3 or 4 is what you should expect to do. All right, let's talk, any questions about this, how to do, I hope that everybody, as I was going around, it looked like everybody felt good about it. I hope that you felt good about it. If you mess it up from time to time, it's easy to mess it up. What I would like to talk about is, how about more than 3 voters? For more than 3, there's actually many more permutations, right? Many more perms. I would like to talk a little bit about how many perms do you expect there to be with a certain amount of voters. How many actual permutations do you expect it to be? Like, how about if we had 4, A, B, C, D, instead of A, B, C? What if it was A, B, C, D? How many perms in this case? I want to try and think this through. this is a question of just sort of counting how many different ways are there to rearrange them. You got to have some sort of system by which you think this through. How can I think of different ways of rearranging them? The way that I would think of it is if I had sort of 4 blank slots and I had to stick one in each position, right? This is the way that I would think about counting up the number of permutations. Each blank gets 1 letter. And we don't repeat the letters, right? You put 1 letter down and then you can't use that one again as you go across. We can think this through in terms of like how many choices are there for how you fill in the blanks in a situation like this. I would say if I have 4 options, A, B, C, or D, then if I just think about filling in the blanks left to right, I have 4 choices for what could go first, right? It could be the A, B, C, or the D. So I'm going to think about in that way. So the first blank has 4 options, right? 4 choices to put in the first position. It could be A, B, C, or D. Can somebody say how many choices would I have to fill in the second position? Yeah? 3, yes. She's showing me the fingers. 3. 3 choices to put in the second position. That's because you've already used one of them, and so you have 3 remaining. So the first blank has 4 options. Then the next has 3. By the same reasoning, the next would have 2 options to put in the third position here, because I've already used 2. There's only 2 left. And then the last one, you really only have 1 option to put the last letter. It's just whatever is left over. So the next has 2, and then the last has one option. All right. So what's the total number of different ways that could go? You have to think about if I make one choice where I have 4 options, and then I make another choice where I had 3 options, and then another choice with 2 options, and then, well, the last one isn't even really a choice. What should I be doing to get the total number of possibilities?
Factorial.
Should I add these together, or?
Maybe like 4 multiple 3 multiple 2.
Yeah, I think we should be multiplying all of these numbers together. This is a basic fact, a life fact. If you're making several choices one after another, and you have, one choice with 2 different options, and then another choice with 5 different options, the total number of ways that could go would be 10. 2 times 5. It's not, you might think you should add them, but actually you have to multiply them. So in this case, we should be multiplying here the total number of choices, or the total number of options, is 4 times 3 times 2 times 1. That times 1 doesn't do anything, but just for the sake of writing this in a pattern, you multiply these numbers together. In this particular example, it's 24. That's kind of a lot, but that's how many permutations you would get for 4 alternatives. Actually, there's a word for this mathematical operation. I heard somebody say it before. Yeah, this is called the factorial. I don't know if you've heard of this. The factorial operation. It means you start with one number and you multiply all the numbers together up to 4, which is what we did in this case. Or you could think of, I start at 4 and then I multiply all the numbers down to 1. All right, this is called, there's a mathematical operation for that. This is called 4 factorial. There's typically not a button on your calculator to do factorial because it doesn't come up all that often in everyday life, but it is an important operation in mathematics in general. This is called 4 factorial, and it's written, there's a mathematical symbol for that. Do you know how to write the factorial?
Excellent.
Yeah, it's written like this, which is a little strange. Like 4! It looks like you're shouting the number, but that's the this exclamation point is the operation. So 4 factorial equals 24, because that means 4 times 3 times 2 times 1. All right. And this is how many permutations you get from 4 options. If you had only 3 options, you would get 3 factorial, which is 3 times 2 times 1, which is 6, which we already saw. Like in our example that we did before, there were 6 permutations. All right. So it is a general fact, generally, for, let's say, n different items, n different things, whatever it is, there are n factorial different permutations. All right, this is an important fact which we are going to use at least one other time in this class, how many permutations there are of a certain number of things. If you have n different things, there are n factorial different permutations. And I will just point out, this number is very big when n is large, right? Like 4 factorial is 24. 5 factorial is 5 times 4 times 3 times 2 times 1. That's whatever 24 times 5 is. And even bigger numbers, when you do the factorial, you get very, very big numbers. Like 100 factorial is 100 times 99 times 98, etc., all the way down to 1. That's a big number. All right? This factorial is a super big number. Can I tell you, actually I wrote this down. If you plug in, for instance, this is very big. For example, 10 factorial, this is just 10 times 9 times 8 times all the way down to 1. This is 3.6 million. If you go to 100 factorial, it's way bigger than that. Very, very large numbers. This is a good classic way to get really super big numbers. We have, in our remaining 3 minutes, I thought I might share with you a strange, this is something you can tell your friends over the weekend about. A strange and beautiful formula. I don't know if you ever have felt like you looked at a formula and thought that it was beautiful. Maybe strange. In my opinion, this is a strange and beautiful formula. This is called, it's from around the 1700s. Some guy was studying factorials and realized actually there's another way to do the factorial. You can do the factorial without multiplying all the numbers. 10 times 9 times 8, that's a pain, and especially if it was a bigger number. This is called Stirling's formula. This is a substitute for multiplying together all the numbers instead of multiplying 10 times 9 times 8 times 7. Stirling's formula actually is only an approximation, but check it out. So this is true for large values of n. N factorial is approximately, it's actually a pretty close approximation. What I'm about to write is what I claim is a strange and beautiful formula. We're not actually going to use this in class, but strange and beautiful because you just have to think about what are the possible things that I might write over here that would be another, like a replacement for just multiplying numbers one after another, 10 times 9 times 8 times 7. Instead of doing that, you can also do it this other way, right? The other way, what's beautiful and strange about it is the other way looks totally crazy. And it will begin with a square root. Check it out. 2 pi n. There's actually a pi in the formula. And then over here, n to the power n divided by e to the power n, where e is another fancy number like from calculus. Pi is, everybody knows about pi. E is similar in that it's a weird irrational number. Anyway, this is a strange and beautiful formula in my opinion because the stuff that you see on the right-hand side has no business being equal to the factorial. Like it's just crazy nonsensical stuff that has a pi and an e in it. But by some sort of magic, the universe we live in is one in which those two things actually, they are the same. They're not actually exactly equal. Because this over here, of course, is not always going to be a whole number. It's usually not a whole number. But it ends up being the factorial. Strange but true fact. All right, I think that'll do it for today. We will have a homework assignment for next week about this Shapley Shubik business.